I'm Gregor Eberli, professor at the Marine Geoscience Department, and today I want to show you the first results of a large project on a fringing reef that did flourish offshore Mozambique during the last glacial maximum. But before I go there, I want to say something about the last glacial maximum. The last glacial maximum, you see here on the graph to the left, is a proxy of the sea level curve assembled with the delta 018. And you see where the modern sea level is, and the last glacial maximum where the sea level was about 120 meters below the modern level during a time of about 12 to 14,000 years. And during this time, of course, reefs did grow on the world's ocean as well, except there was quite a little bit of fresh water taken out of the oceans at the time, and so we still don't know much about what these reefs looked like. They did the same assembly of the coral species and same chemistry in it. Well, why don't we know much about it? Well, the reason is, of course, that when the sea level was 120 meters lower, all the coastlines were way out into the ocean, and today, these lowstand reefs, as we call them, they're covered by sea level, and you have to core them down to actually retrieve the record of these lowstand reefs. There's only about 3 or 4 places in the world that they have been drilled, and one of them was drilled offshore Mozambique in the Mozambique Channel, where this reef built a fringing reef along several hundred kilometers along the coastline. And when we look at the multi-beam bathymetry of this area, it looks like this. You see a reef terrace down that has a crest about 94 meters, goes down to 140 meters, and then a flat terrace goes back and has a second reef terrace further back. So this first terrace, this potentially has grown during the last glacial maximum. When we look at the sea level curve at the time, you see that the sea level was down to about 140 meters. Mesophotic reefs, corals could grow there, and then it will probably drown during the meltwater pulse 1A. And so I was involved in this project not because it had this we could study these coral reefs during the low stand, but actually they wanted to know how stable is that, because they wanted to do some underwater installation on that. And for this, they drilled quite a few cores. They drilled 12 cores, 6 on the lower terrace, 4 on the upper terrace, and 2 on the offshore of the reef terrace itself. They drilled it with an apparatus that sits on the seafloor, has a revolving set of core borings, and it goes down pipes, and they bring them out, and they bring one after the other out remotely from the ship. It is drilled. The deepest core they took was 120 meters. The one that I'm talking today about, this was 67 meters down, and the core recovery was about 87%. So this is an incredible high recovery through a coral reef system. When I worked on this, I was involved because they looked at how stable this whole system is. And I said, well, once you're done with that, could we have the cores? And I made a request to the government of Mozambique. After 3 years of waiting and probing, eventually we got the permission to work on the cores, and all the cores are now here in Miami. It's really a treasure trove that we got from Mozambique. But not only that, they did also do some 3D seismic data across it. So we also have the geometry of this fringing reef. And you see here to the left the picture 2D inline of this 3D seismic data set. And you see the geometries of it. You see that this is like a prograding system that works its way out and then up. And where the blue dots are, these are sort of the edges of the coral reef as it goes down, as we go into the last glacial maximum, the deepest sea level part. And as the deglaciation starts, how the reef follows up the sea level as it rises up before it can't follow it because the sea level rises too fast. Here to the left, we see the core recovery, and indeed the core recovery confirms that interpretation of the seismic. And Wright has a poster up there, and I recommend to go and look at the cores. And Pulina Manekas looked at the sediment composition of it, also on a poster that you can see. We dated it, and Merrilee Rivers, with the uranium thorium data in Ali's lab, actually confirmed that this is grown during the last glacial maximum, starting at 34,000 years, and indeed drowned at 14,000 years with the onset of the meltwater pulse 1A. Klaus looks at the at the corals in this whole system. And I'll just show you some of it. So he looked at the corals in 1.5 meter intervals, that's each core length, and he found 328 corals in that core, and basically 8 specimens per interval. The bottom portion was on the slope, didn't have much corals in it because it was on the slope. So when we look at these, Acropora was basically dominant, and in the fore reef area, it was more the tabulate forms, but very much the same as we have today on the coastline for Mozambique. The reef crest itself also had like the more robust corals. You see one here that has a lot of the borings from Litofago in it, and was more robust, again, pretty much what we have today in the world's oceans. The back reef area had the beautiful Galaxia, quite some of it. It is very nice little corals. You see them in our core, they sometimes fall apart, and you have individual little cigars of these corallites. So in summary, from these corals, he identified 28 morphotaxonomic groups belonging to 22 genera, and had mostly Acropora was the dominant genus, a tabulate, branching, and robust corals. So overall, it was a beautiful fringing reef with a high diversity of corals. And actually, there is not much difference from the species of what we had today. But what was different in these fringing reefs is that it was associated with microbialites. So the microbialites are this microbially induced precipitation. So there was a microbial community living in these coral packages, and they made incrustation of all different types and forms. And I show you some just over here. Sometimes it was just like a layer, little layers, and here these gray ones. Other kinds you see the coral in algae, and then the microbialite in between, and the microbialite on top here. In other places, it grow into the cavity of the reef. Sometimes with these digitate forms, just go upward and upward, sort of like mini stromatolites, but very dense. When you look from the top down, it looks like this. Or in other places, on larger cavities, it just grows from the top and the bottom into the cavern or the cavity of the reef and builds this very dense framework on the reef itself. Even within if you take a thin section and you look onto the skeleton of the corals, you see the coral itself, and then the empty spaces are partially filled by these little fuzzy brown dots, which are this microbially induced precipitation in the coral reef itself. So when you look at the beginning, you thought, well, that might be contemporaneous. You have the microbialite growing at the same time as the corals. But as it turned out, that was not the case. The microbialite grows, lags, the coral reef grows. In most cases, we see the coral, then a calcareous crust, algae that encrusts it, and then the microbialite on top. On the sample that we did here, we looked at the age difference between the two, and we found about 500 years. In a core that it drilled in Tahiti, in one of these last glacial maximum reefs, they also found that this microbialite always lagged. The coral grows by 120 to about 500 years. So it's also behind, but they all occur during the last glacial maximum. Interestingly enough, on the upper terrace, they're not there anymore. In the modern system, they're not there either. So there is something in the world's ocean, the alkalinity, it must be different, that we have this intense microbial growth during that time. So just to say, the Acropora is a dominant species among all that. The biofacies reflects the over and shallowing upward trend, and the microbialites occur in very various form, and they're an integral part of the reef system and actually make it very, very hard and stable. And they don't occur in the modern reefs. The coral biofacies also is very important because we know now exactly where it is and how they relate to the sea level, and with that we can actually interpret the last glacial maximum, the evolution of the sea level, and the rate of sea level rise to when it will occur. So just to go back one more to this figure, because the last glacial maximum was not just going down and up. Many things happen in there. We know this from ice cores in Antarctica and in the Arctic. And from other areas, we know from the North Atlantic that we had these Heinrich events, this fast-growing ice sheet movement that would bring sediment out in the North Atlantic. We have warm periods. Then at the end, we have the meltwater pulse 1I, and we have the onset of the last glacial maximum as it comes down, that we think we can see actually in our seismic data how stepwise it goes down and then how it goes up. So overall, with the seismic and this core, we have a wonderful data set, and not surprising, half of our department now works on it. So we have, together with Will and Pulina and Jara, we will do the core analysis, the seismic interpretation. Ralf does the petrophysical analysis, and Klaus, with scientists from Mozambique, will look at comparing the modern and the ancient reef or coral species and assemblages. Amanda has used the core in a class and looked at the different components, the chemical composition of the different components, and we'll continue to do that, and also on the different microbialites. Sam Goldberg and Merrilee Rivers will try to reconstruct the sea level using the corals and the age dates, and then the GI modeling to get a really good sea level curve in the Indian Ocean. And Benjamin Ross, he's a benthic forum specialist. He looks at the benthic forum assemblages, and he will also pick us the forams that we think we can make a high resolution series of the chemical stable isotope composition in the Indian Ocean that we can compare to other records from the ice sheets and from the glacier and so on. Thank you very much.